We're continuing our unit on exponential and logs, and these functions can be plotted in a better way than lines of best fit using regression lines, and we're going to use technology to do that. They are based on mathematical formulae and mathematical algorithms, but we're going to let technology do the work with our course, and we're going to look at semi-log graphs in this video as well. So drawing a line of best fit by eye can often be inaccurate, okay, and we saw that it can happen, the inaccuracy can be during the construction, and it can also be imprecise, like we saw in the previous video, to have a line, even if that's a good line, and then determine 2 points that seem to be on there. There's potential there for imprecision and inaccuracy. And superior is the method of least squares regression. So least squares regression, basically we're going to use graphics calculator. Desmos also does a good job at this, or other similar stuff. Excel can do it. So we're going to show it using the TI inspired graphics calculator, and the results of the line of best fit using least squares regression, they basically come from the squares of the distances, and that allows for points above and below. In other words, it eliminates negative values when you square it, and the idea is to create a line where the distances above and below are minimized, so it optimizes that in a sense. We're going to have a look at the data from the previous video. You need to be familiar with that, and that's the example where it's running times for the 1500 event for women arbitrarily since 1960, and we're looking at how well that fits an exponential function. And we basically use a semi-log approach. We change the y variable, i.e. the dependent variable, into the log of the dependent variable, and it converted the exponential or apparent exponential into an apparent linear function. Let's have a look at doing that, doing the section where we sort of formulate the equation using technology, but instead of the by eye part. So you'll remember that we had this data you can see in the top left of your screen, and I'm going to enter that into the TI Inspire. There we go. So the data is now locked in. Hit menu and statistics, and we've got statistical calculations, top one, and then we go to exponential regression, and we choose what we want. I've got in my X list, I have years and running time. Save the equation to function 1, that's fine by me. There's only one of each, so frequency list stays at 1, and then bang. So let's have a look at that. We've got some interesting stuff there. So I'll just make the columns a bit wider so we can see the information properly, and may do that even more. Okay, I'm pretty sure I've got all the decimal places there. Now I had my diagnostic turned on to earlier, so I don't think I can get to it from the screen. In settings for regression, I had my diagnostic switch on. That'll give you an R squared value. It's not brilliant at 0.716577. It's okay. So it's in the form AB to the X. We're working in the form y equals AE to the KX. So this is an important thing that you need to do. So what we're going to do is grab the A and B values there and work in this space here. So we've got A and B. Okay, I want that to stay as lowercase a. That's B. This is an important step, especially if you're using a Texas Instruments. Okay, we want to compare it ultimately of what we got in the previous video. You might remember that you can see I've pasted there. You might remember this. Hopefully you do. That's what we got using the by eye method, and we want to convert it into this form here, and it's in the a b to the x form. So then we want to be able to compare the regression result with the other result. So this is an important step I'm about to show you using our values. So this data here, y in the form y equals ab to the x, even though we've been using base e lately and natural log, that form of an exponential is actually familiar to you. We've also got come up with an equivalent a e. Now this is where we've got to be careful. A to the kx. Let's understand that a equals a because of the following. So using the first equation, take logs of both sides, using log 1 using log 3, we get that result there. If you use the work from the previous video, what we got with the base e was, you remember this, so there was obviously some working that occurs before this. This isn't just out of thin air. Remember, you've got to go back to that previous video for it. But yeah, basically we have some equivalents here. Alright, we have kx, and you can see that up the top there. On the top left in blue, you have that form that we were using last time. Okay, don't get confused with that capital Y. That was the independent variable. So again, a equals a. So lowercase a equals uppercase a. It's pretty obvious. They're constants. As far as the other goes, we shall have a look. That means k must be the same as log b. So let's have a look at that with these values here. Now I'm not going to shorten them because it does make a difference. Spoiler alert, so we've got an answer there. See the difference? You might be tempted to shrink that down to just 3 decimal places, but it makes a difference to our answer. So we've got y equals, for our form, starting off with 248.559 times b to the b, which is 0.997 to the x. It's equivalent to y equals 248.559. Looks like a decimal point there. It's a stray dot. There we go. Fixed. E to the kx. So see, the 248 is the same value for upper and lowercase a anyway, because when x is 0, the e to the kx will make that e to the 0, which is 1, and the b to the x is b to the 0, which is 1. So they're the initial values as such, so they will stay the same for that reason as well. So looking for an e to the kx. Okay, so dispensing with the a's because they're a known, we've got 0.997, etc. to the x equals e to the kx. Logs of both sides. Okay, you can see what's happening there. Using log law 3 and also the fact that natural log of e is 1, we have x times log of 0.997, etc. equals kx. So we got negative 0.002517, so negative 0.02517, got that there, equals kx. So you shouldn't say we're dividing both sides by x, because when x is 0 you're dividing by 0. Don't say that, but that equates k with 0.002517, and so we have to update our expression. You can avoid this whole thing actually probably by using from memory. It caught me for a little bit of lack of research. I'm pretty sure Desmos would probably use base E. Check that out. Excel or a Casio calculator, I'm told, but let me know about that. I'll probably, by the time you send me a message about that, I've probably found out, but I'm pretty sure about Excel, pretty sure about Casio, and I can't remember about the Desmos, but I reckon it does. I'll find out after I make this video. So a e to the kx would be 248.559, etc. e to the negative 0.02517 x. Now, to be accurate, remember we had the variables, it was t and y, so capital T and capital Y. So to be correct, t equals 248.559, etc. e to the negative 0.002517 capital Y, and I just nicked away without you knowing, and that's from an Excel screen dump, and that's from Casio. I still haven't checked that, but Desmos is such a good thing that it's probably good. Let's see, let's compare our answers to them. So 248.55, yep, that's good. Negative 0.002517, yep, rounding maybe, but that's pretty good. So we've got an answer. Now we can just sub in if we like, or we can add graph, and we had that saved into it's not converted, but it's saved into F1. We could put the other one in F2, it'll plot the same graph. So just plotted F1 and got the window right, and found out that was 213.72. So just borrowing that and pasting that in here, hopefully, and comparing that with what we had before. And back on the previous video we had 213.8 rounded, and we've got 213.72 roughly, so a little bit of variation, slight improvement there. So the regression gave a slightly better answer, but you know what's really interesting is that if you rounded too short, you you got to be careful here, because the Casio and the Excel give quite different answers due to their rounding. You can sub in to try it yourself for when y is 60, because you might remember from the previous 2020, you remember, was the year, and that was 60 years after 1960, and that's making a sub in 60 there. There's quite a difference between the two of them. It's about 5 seconds, I think. So it's, while the regression in this case gave us a more accurate answer, you can lose a lot of precision by not rounding your by rounding too much, I should say, by not rounding appropriately, being too drastic with it. Now, in the final part of the video, we're going to look at one method for identifying exponential functions, because there is a thing called exponential regression by plotting the original function and not converting it. But we want to teach you multiple weapons, I suppose, and this is one of them, and you do need to know this along with using the exponential regression of the exponential. We want you to also be able to convert it to a semi-log graph, which is what we've been looking at. So it says here, while many phenomena are indeed exponential, especially a lot of natural ones, sometimes we might infer that they are, and it might not be. It might not turn out to be exponential, or it might be a weak exponential model, or debatable. So exponential functions may be identified. One weapon in your arsenal might be by plotting the logarithm of the dependent variable against the independent variable, which is what we've been looking at, and that's one of the ways we expect you to be able to identify exponential functions. We plot the log of only one variable. That's why it's called semi-log. Okay, so we're talking about the vertical axis, the dependent variable. Okay, and it'll give a straight line with a slope equal to the exponential constant k, and a y-intercept equal to log of a, the initial value, which we've been seeing. Let's finish with an example of this. Not completely new, because it relates a bit to the previous video. So we got the amplitude of a pendulum, which is basically its maximum swing from its rest point, is observed to vary over time as shown in the following table. Draw a semi-log graph and use it to determine whether the amplitude is an exponential function of the time. So what we got some data there, minutes in amplitude and centimeter. That's t versus s. Alright, so what we do is, because we've got the dependent variable s, we find the log of that and we add another row to the table there. So we draw the graph there, scatter plot first, then you'd either draw the line in either by eye or using the regression. So like previously in the video, you come up with the formula and plot the line based on that equation, and you can see they've got one there, and we've got a straight line with, looks like it's reasonably matching. You might be able to back that up to verify that with your R squared if you've got your diagnostic turned on. So your R squared is like verifying through the use of technology. Remember, something that's approaching 1 is good, but something that's like 0.6 is weak, quite weak. Okay, so you need to talk about that if that's something you're using. But anyway, looking at it does appear that, like, even if we don't look at R squared, it does appear to be pretty good correlation there. If we look at the points, there's not a lot of deviation by inspection there, so looks fairly good. Now the rest of this example assumes that you haven't used technology and using known points or certain points, so 1 and 2.48. Now they've gotten those from the table this time, okay, a bit different to the previous video where they didn't choose given data, they got the ones from the line. You could still use that method as well. And 10 2.2, so they got decent values because all of those are pretty close to the line. They figured, it's reasonable to just grab those values there, but you could also get values like that one there because it's it's pretty certain and it's pretty convenient, and maybe that one there, and there's other examples, there's another one there. Okay, so this example is assuming we're not using the technological approach, and using our gradient formula we get a gradient of -0.31, which corresponds with a falling line, as you can see, and it's our k value, so that becomes our y-intercept, our gradient, I should say. Now for the y-intercept, it's about 2.51 by inspection. If you had the equation through regression, you'd be able to do better than that, but you can see it's just above 2.5 there, so 2.51 is reasonable. So to get A, we write an exponential form. It comes out at about 12.3, and we're subbing in as we have done in the past there. So there's one way of getting an answer, and it appears to be fairly good. This is a low-tech solution. Okay, again, you could use R squared and least squares